So, hi, good evening, everyone. Yeah, we'll start from the antenna impedance and all. So, before that, I want to ask you, do you have any doubt or anything on polarization and whatever we discussed yesterday? Do you have any doubt or confusion? No, then okay, we'll proceed from here. So, our first topic of discussion is input impedance. So, when we discuss about input impedance, we have to model the antenna as a we will model it as if it is a lamp parameter, although in reality it is not, but we model it as a lamp parameter. Okay, so we take it as a impedance which has inductance or capacitance equivalent as well as some resistance. So that is what is shown in this picture. So the top left side picture, it shows the antenna with terminals A and B, which is fed by a generator with impedance GG. Okay, ZG, and the equivalent Thevenin equivalent circuit is shown there. So VG is the generator voltage, RG and XC is the GG of the generator model, and the antenna itself is modeled as, you see, two resistance RL and RR. Okay, so RL is the loss resistance of the antenna. If you see, yesterday we discussed that antenna has some conductance and dielectric losses. So there, those will be modeled as RL. Okay, and the R is the radiation resistance. So this radiation resistance is the most vital part, because these models the amount of loss happens in antenna because of radiation. So R is the part important or relevant for radiation. Okay, and Xa is the amount of inductance or capacitance antenna provides in its terminal. So you always see, like, we are talking about the terminal AB. In that portion, if you see how much you will see. Okay, so here it has been modeled as, ZA is the uh, antenna impedance given by RA plus JXA. And RA is the obviously is a series resistance of RR plus RL. And now if you take the very simplified circuit diagram, that gives the current IG is given by VG by GT, and where the whole impedance comes from the circuit part, I mean generator part, as well as the antenna part. That will determine how much current will flow from generator to the antenna. So there, that's why we have a resistance part as well as some, the inductive or capacitive part. So altogether, it is modeled like this. Oh, okay. So yeah, any doubt on this?
No, sir.
Okay, okay. So we'll move to the next slide. So you remember this model, okay, because it's very vital to analyze. Now, now the question comes: why are we modeling like this? Yeah. Uh, Let me ask you: why are we modeling the circuit? The modeling the antenna as circuit equivalent or Thevenin equivalent. What is the reason? Or why the input impedance of the antenna itself is important?
Power transfer.
Ah, right, right. So the thing is, like, if the antenna impedance matching does not happen properly, so some portion of the wave or the voltage, it will like get reflected from the antenna terminals. So that we what we saw yesterday, right? It was the mismatch or radiation mismatch that was modeled as 1 minus gamma square. So that was the 1 minus gamma square was the factor getting delivered to the antenna. So some portion was reflected. Generally, we measure all these things as S11, S parameter 11 at the antenna terminal. Okay. So all this comes from there. So we have to get maximum power transferred to the antenna. That's why input impedance is vital. So now we see we do the simple power calculation from the cyclic theorem. These are the various the powers. If you take different components of these circuits. So first part is radiation resistance. So how would you calculate that? It takes more absolute value of Ig square and it multiplied by RR. Okay, RR is the radiation resistance. So from the previous formula, previous in the previous slide, the formula we had from Ig, that if you put, so this gives you the values of power delivered to antenna for radiation. Similarly, you can take the power dissipated in antenna as heat. Why this is dissipated? Because this takes RL or the loss in the antenna itself. That's why this power will be radiated in the antenna. So this can be similarly calculated from current and radiation loss resistance. And there is another part is called power dissipated as heat on internal resistance RS of the generator. RG of the generator. That can be also calculated. Okay. So now these are when we have all these powers. Now we will do the maximum power transfer on this. In what condition maximum power from the source will be transferred to the maximum to the antenna. Now see what it says. As you know, I think this is the very basic theorem you know all from your bachelor study. It says for conjugate matching, we need the antenna to resistance part, the real part of the impedance equals to Rg, and Xa equals should be minus Xg. So that is obviously the simple condition of conjugate matching. If that happens, then the power for radiation loss and also in the RG, or that means in the generator itself, those powers can be calculated. So they have been calculated, and in the right side, the equation shows that PG equals PR plus PL. Okay, so that means the power in the generator is equals to power in the antenna, total power in the antenna. So obviously, in the normal circuit theorem also, if you use maximum power transform, so that will show the same thing. So half power is already dissipated in the source itself, and rest half of the power is delivered to the antenna. And out of that, some portion is radiated and some portion is lost in the antenna itself as heat. So this is the very simplified, calculation, but it's very much important because from this you can calculate, you can have a basic understanding how the power goes or dissipated in the antenna itself. So now, yeah, any question on this? Any doubt or anything? So thing to notice here is that all this has been, this page or the previous slide also is done for transmit antenna. So that means for transmit antenna case, a source has to provide power to the antenna, right? Then only antenna will transmit. We can also take the reverse case when we have a load connected to a receiver antenna. That means antenna will collect power and then it will deliver to the load resistance. So that we will calculate later in next slide. Okay. So now says if we apply maximum power transfer to receive antenna, what happens? So yeah, now I will ask you a question. So what do you suggest? If the antenna receive antenna has some power from somewhere, it will obviously collect some incident power. So what would happen to it? What are the components it will be? Yeah, anyone?
Once,
No, yeah.
question once more.
So I'm saying if a receiver antenna collects some power from somewhere, so how this power will be dissipated or what will be the different components? Yeah, it's written on the slide only, but you just have to visualize what happens. Somewhere, let's say antenna working as a receiver. What will happen?
Will
Yeah.
dissipate as heat. Some.
Mm-hmm.
Yeah.
Okay, that is one portion, and others. Maybe Bhargav.
Some part may get reflected back. I mean, at the
Okay,
receivers.
why that happens? Why will be reflected?
Like if there is some impedance mismatch.
Mm-hmm. Impedance mismatch. Yeah, right. Yeah.
At the receiver side.
Mm-hmm. So it will be reflected from which portion? Which portion exactly will be responsible for that? See, the important part is if the antenna works as a receiver, so the power will be delivered to the load, right? But now the load will be connected through what? A transmission line. So you must always remember the antenna is always connected to a transmission line. Okay, just like any circuit or something in any antenna, there will be some kind of other transmission line or other kind of microstrip line will be connected. That will deliver the power to the load. Okay, so as you said, as Bhargav said, so when this power is received and power is delivered to the transmission line, there will be some mismatch of impedance in the junction of transmission line and antenna. So that's why some portion will be reflected from the junction. And that power will, what happen? That power will work like input to the antenna, input to the receiver antenna itself. Okay. Although it is a receiver antenna, this reflected power will act as a input or as if a source is connected to the antenna. So this portion will be again transmitted by this antenna. That is one of the main components here for the receiver antenna. And the other components, obviously, the some portion will be delivered to the load. That's what we generally are interested in, that component. How much power is delivered to the load? So here you see all these four defined components has been calculated. Okay. So we are also considering here that conjugate matching is happening. That means the total resistance is also same as the load resistance, and load inductance is same as the inductance or capacitance is conjugate to the same to the one in the antenna. So now there says total power induced or collected or captured power is given by half of VTIT. Okay. So half VTIT is the VT is what is the voltage at the terminals AB, antenna receive terminals. Okay. So if you take that, that gives you total collected power. Now out of that, this collected power, what happens? So some of the power is delivered to the load that has been calculated, and some power is scattered or re-radiated that has been termed as PR, and the rest of the power is dissipated as heat. Okay, so that portion, that loss will be in the load as well as in the antenna itself. Now if you add all these three components, this delivered to load and scattered power as well as dissipated power, all three summation will give you total captured power. Okay, so yeah, is there any doubt here? Okay, so now that we have these powers and all, how do we take this into account? We are not going to always calculate, the current and voltage and all this. There are other terminologies in antenna that we will take care of those. So those are called antenna equivalent areas. Okay. So that means, antenna will have some physical area. Okay. So that physical area is actually, relevant or important for how much power it will actually transmit or actually collect. Now, out of those total area, some portion, it has different components as you have seen. Some lost, and there are some scattering, or some captured. Okay. So now what it says, before that, I would like to, you guys see this equation in the box. In the right side, there's a box. So how these areas are all connected? Why they are vital? If you remember, yesterday we discussed about the power density, right? So this power density is Wi. Okay. So because in antenna we always work with power density, but actually what component we are interested in, the power, total power, let's say. So this power density as well as the area, antenna aperture area, will give you the total power. So that's why these areas are very important. The concept of areas are important. So I guess, do you understand why the area, how we will use these areas, concept of areas?
Yes.
Okay. So it is just, the simple calculation of taking the ratio of power divided by power density. So power density is same, power given by over a unit area. So now that can be calculated from, current and terminal resistance and all those. So equivalently, this same equation can be used for all the other areas. Now let's see. You remember this calculation here is given for the receiving mode. Antenna, for a receive antenna, it has been calculated. Okay, so it says what is the maximum effective aperture area? Maximum effective aperture area is given by, it calculated from volt total power given by RT. So that means so we'll see, go to the last slide. So what component is that? So you see this is the PT, or power delivered to the load. This component is important. So this component we are taking for maximum effective aperture area. PT, power delivered to the load. So here you see this, the same equation has been used, same formulation. That means maximum effective aperture area is given by what would be the power delivered to the by the antenna aperture to the load. So that is the equivalent area of the antenna. Although the physical area is more than that, only some portion of the area is actually, it leads to the area power delivered to the load. And rest is scattering area. Scattering area means what? So out of the whole physical area of the antenna, receive antenna, some will be leading to the scattering or re-radiation. That is what giving to this area. Loss area is the what happens. The loss happens in antenna itself, conductive dielectric loss. And the capture area is collection of all these three areas. Okay, that's why in the bottom it says capture area means effective area, sum of scattering area and loss area, all three together. But the important part of this is the maximum effective aperture area or effective area. Okay, why? Because this is the area what gives you how much power is delivered to the load. Rest of these are not that much important. You just have the concept, but we will use the effective aperture area. Is it understood? I hope you understood this. Yeah. So now the important part is why we are talking about all this, how this all connects. So here it says we have a very important connection between directivity and effective area. Okay. So what is that? We have something called aperture efficiency. What is aperture efficiency? Out of the total physical area, only some area is giving the power delivered to load. That is what we call effective aperture area. So if we take ratio of these two, that gives you aperture efficiency. Okay, so that is one way to calculate how much of the physical area is efficient for delivering power to the load. Now see, now it says the effective aperture area of the antenna is related to the dielectric, to the maximum directivity D naught is given by the formula by lambda square by 4 pi D naught. Okay, so this should you must remember, because this is the so it is of very good importance in antenna theorem, because always we use this equation. If you either know the directivity, from that you can calculate the aperture area, effective aperture area, or if you know the vice versa, if you know the aperture area, you can calculate the directivity. Okay, either one of them is important, relevant. Now it says, it always is talking about maximum directivity and maximum effective aperture area. So what happens if there are other kind of losses? There it says, the previous equation, it assumed that there are no conduction dielectric losses. That means ECD, or radiation efficiency, was unity, and the antenna was matched to load. That means the reflection coefficient was the unity, and the polarization of the impinging wave matches to the antenna. That means polarization loss factor was also unity. Okay. Uh, yeah. So I think the reflection efficiency would be 0. It is wrongly written as unity. Okay. So all these three components, three lossy components, has been taken as to minimize the other losses. Now, if that does not happen, they will also contribute to the effective aperture area. So in that case, you cannot just directly take the D naught or directivity for calculation. So there you have to take all these three components also. So yeah, I hope now we can see like how they are all taken. So E naught is the total efficiency of antenna that has ECD as well as 1 minus gamma square. That is the reflection mismatch loss, and the rho rho omega dot rho a. This is the polarization loss factor that we discussed yesterday. So if you have all these three into account, then the effective maximum aperture area will be given by this equation. But generally, we take the previous equation only. But in some cases, you have to take more general thing. Yeah, anything? Is it clear here? Yeah. So now we come to very important equation that's called Friis transmission equation. So the beauty of this equation, if you see, this is the paper Friis wrote. It's like almost before our independence, it's May 1946, right? So almost like 70, 80 years back, he wrote this, and that is this equation is so simple, and this paper was only 2 pages paper, and this is like always prevalent in today's communication or any power transfer theorem everywhere. It is so prevalent. So do you know what IRE is? Anyone has any idea? IRE, this was published in the journal IRE. Yeah, you did not have any paper before from IRE or somewhere?
No.
Okay. So IRE stands for Institute of Radio Engineers. So this is the IRE is the mother of IEEE. So now around, I guess, 1960 or 70, the IRE has been transformed to IEEE. Okay. So in today's omnipresent IEEE was IRE before. It was called IRE. So all the old papers you will find, like in this age, 1950s and all. So those were called IRE journal, Institute of Radio Engineers. So I would tell you to look into this paper. It just even the paper heading is called a note on a simple transmission formula. It is that simple only 2-page paper, and but it was groundbreaking for those days. Even now, everywhere it is used same formula. So please look into this paper. You will find how how much insightful it is. So yeah. So now let's look into what Friis transmission equation is all about. So what it discusses is that, let's say there is a transmit antenna and there is a receive antenna somewhere in the far field, far away. Okay. So if we transmit some amount of power through antenna, how much power will be received? Okay. So yeah, now I will ask you this question: why this calculation is required? Why is this relevant? Somewhere a transmit antenna transmits and receiver antenna will receive. Why will you calculate? I guess if you have a
to get how much power is received by the receiver.
Depends on
okay.
the distance between the transmitting and receiving antenna. Is that?
Distance we will know, but why is this power receiving is important? Why is it vital?
For receiver sensitivity, like receiver should have some minimum limit so that we can
what
noise.
is that limit called?
SNR,
exactly.
like for SNR calculations and all.
No, yeah, it has a name to it. Anyone who from communication background, you will know it has a very nice name in communication.
Receiver
so you are
sensitivity?
not from communication. Yeah. Yeah, Bhargav, you were saying something.
Receiver sensitivity?
No. It's called link budget calculation. Have you heard it? In communication, they calculate it. Link budget. So this is called a link between a transmitter and receiver. Okay. So why it is important? So let's say now, last week only we sent the Chandrayaan to moon, right? So it has few antennas there. And now from Earth only we are receiving. Okay. So how do we decide what kind of antennas to choose? So any calculation itself, how to choose what antenna to select, what are the things, what would be the parameters? Okay. So it all comes from the basic thing called SNR, or no, its basic thing is like bit error rate. Okay. In antenna communication, antennas will be used for what? Mostly it will be used for communication, right? Data communication. So data communication, what is the terminology for comparing the communication is called bit error rate, or BER. Okay. So let's say this antenna in the moon, we have to receive the signal from there to here in the earth. It is now sending, very important sensor data and all this. Now we have to receive this within some error threshold, within some threshold BER. Okay. So for that, we have to calculate now what should be the SNR, or a signals to noise ratio, in the transmitter and receiver correspondingly. So noise power we will know, because we will fabricate the antenna accordingly, how much noise it will be used and all this noise factor we can calculate. And now we have to see how much signal should be transmitted so that this SNR can be maintained. That's why this signal calculation is nothing but the power calculation. So this link budget calculation is also it comes from this only, Friis transmission equation. So all comes from how much how good a link you want. Generally, in antenna, in normal communication, we take the bit error rays as 10 to the power minus 5 or 10 to the power minus 6. Okay. So accordingly, we calculate what should be the SNR and what should be the power transmitted. And for that, power transmitted also, if we have to first see from Earth only how much power we should transmit, how much megawatt or gigawatt power we should transmit, so that it will receive there. And also, in the other end, we have to design our, the solar panel and all in the satellite itself, so that it can calculate, how much power it has to transmit from there. From Earth, we have, lots of resources. We can just take amplifier and increase the power transmitted. But in the moon, what we have sent is a tiny device, right? We don't have lots of power. So what would be important there? They will be sending the data to us. We are receiving end. Okay. Receiving end, we can do many things on Earth. But on the transmitter side, on the moon, why it is important? Because there you have to, very carefully select the antennas. It should have very high gain and all these things. It should have lower noise, because there you have, very minimum power generated from the solar panels and all this. Okay. Yeah. Do you have any question on this?
So can you explain that link budget formula, which means is it a for
No, I am not talking about the formula itself. I am telling you how it is all related. Why all this
Okay.
power calculation is required. That is what I am telling you.
Okay.
I mean, did you understand why? So generally for communication we will be using, right? So communication means what? If you transmit something from somewhere else, you should not receive, something else. Your, let's say your friend from Kerala is talking to you over phone, and you are not, you cannot listen to him properly. That means lot of noise is there. So obviously we will not prefer that kind of communication. So you should have some bit error rate threshold. Over that, you will have, obviously the link will be sufficient. So for that SNR calculation is done, and for the SNR calculation we see how much power is required, and for the power we see what kind of antenna can give you this kind of gain and all these things, or minimize the losses, so that you can have the power calculation.
Okay,
So it means from the received power, we'll calculate the SNR, and with that we'll check the bit error rate. So if it is meeting our specs or not. So based on that, we'll be taking the antenna what we wanted, the transmitting.
Exactly. Yeah. Okay. Yes. Yeah. Right. Okay. So now let's come back to this equation, phase transmission equation. So yeah, that's what I was telling you. It is so beautiful that only very simple equation, but it is prevalent everywhere nowadays. So it says, the picture shows two antennas. Left hand side is the transmitter with all these defined characteristics. PT is the total power transmitted, GT is the gain, DT is the directivity, ECD is like the losses in the antenna, antenna efficiency, and gamma T and rho T, these are the antenna polarization vector. Rho T is the antenna polarization vector, and gamma T is the matching factor with the antenna and transmission line. And all the similar things has been calculated in the receiver antenna also. Right? Now, the antennas are not placed, directly front to front. Okay. Obviously, if you have your antenna here, your mobile phone has an antenna, and the base station has the antenna somewhere. They are not properly aligned. Okay. So that's why this theta phi is different. Now let's say what it says, that you have an effective area of the receiving antenna. How is it calculated? We had the formula before, right? That takes care of the D, directivity of the receiver antenna, and lambda square by 4 pi, as well as it takes care of the ER, or the losses, efficiency of the antenna, right? Now it says, but you see, we are ignoring the gamma or the reflection loss, polarization loss. Those now we are ignoring. But later we will see it can be brought as a general form. Okay. So just not to complicate everything at one go, we are removing some portion of it. So the effective aperture area is taking only the losses in the antenna. Now it says power density of the antenna, transmitting antenna. So, the transmit antenna will transmit how much power? it will be given by PT into GT. So what is PT? And now the GT. Now, yeah. So now I will ask you a question from yesterday. We had discussed, the power gain, antenna gain. Okay. So from that, can you tell me what is the PT? PT is what power here? In the
Radiated power.
Is it so?
Transmitted power.
Yeah. Guess again. I am talking about the transmit antenna. There only PT is defined. Yeah. But yeah, better I will ask you, what is GT? The gain of the transmit antenna, what is it ratio of? So yesterday only we discussed, right? What are these components? Two components of power. Is the ratio of that gain.
PT is the average power, right?
No, not about average. I am talking about, in the transmit antenna, there are two kind of powers. That ratio is given as gain. What are these two powers? How is gain defined?
The power radiated to the total power incident.
Total incident? What incident? It's talking about transmit antenna. In the transmit antenna, what happens? There will be a source or generator that will deliver some power through transmission line to the antenna, right? So this will be the power delivered to the antenna. That is, see, these the basic terminologies if you don't understand. So there is, you will face a lot of problems again and again. So that's why you must, know what gain and directivity, all these things are. Polarized. What does it say here? So gain is ratio of what? Radiation intensity and given by total input power or accepted power. Remember this picture? We are talking about two references. The left hand side reference is how much power it accepts, and the right hand side reference is how much power it radiates. Yeah, do you remember this now?
Yes, sir. Yes.
Yeah, so now from this, can you tell what was that power PT? We are, before that, what are you calculating? We are calculating, let's go back. We want to calculate what is the power density transmitted by the antenna. So obviously the transmit antenna is transmitting power. For that, at some point we want to calculate what will be the power density. So that means the power we are interested in is the radiated power. Okay. So this yeah.
So this PTGT is the radiated power, and this PT is the power delivered to that antenna.
Exactly. So PT is the total power delivered to the antenna in the antenna transmission line junction. Okay, so that is the collected power by the antenna, and out of that, some power is actually radiated. Not all the power. Why not? Because antenna has losses and all these things. Some portion of this antenna power is actually radiated. So out of that, how you calculate the now power density? You take 4 pi r square at a distance r from the antenna. You want to calculate. So this r will be in the far field of the transmit antenna. So now it is very easy. Now the GT has been replaced by the simple and equation of GT is given by ET into DT. As you know, directivity is how it is related. Is this equation clear? Because everywhere you see, in many cases you will see this equation, but it should be very clear to you. Why we just take like that? Yeah, Nandana and Pavan, to you, is this clear?
Yes, sir. Okay.
Okay. So Okay. So means like how much power we collect, how we provide the antenna, and how much it actually radiates. Okay. So from that we calculate power density transmitted by the antenna. So now that what happens, now that it has this much power density in the receiver also. The receiver is at a distance r, right? So at the receiver location, we have transmitted this much of density. So now this density will be collected by the receiver antenna aperture. Okay. So this power density will be impinging on the receiver antenna and it will be collecting this power. So how to calculate that? No, this is very easy. We already had the equation of effective aperture area of the receive equation, and we know the power density. So from that we just take what? Power collected is effective aperture area multiplied by the power transmitted. Density, power density transmitted. So that is only the second equation shows. Effective area multiplied by power density of the transmitted antenna. So if you take all these things into outside now, then the equation becomes like that. So they have the how they did it is like now the W2 WT has been replaced by the first equation. If you do that, it becomes all the other components. Now you have DT and DR, both the directivity of transmit and receive antenna, as well as ET is the losses or efficiency of transmit antenna, receive antenna, both of them. And rho T rho dot rho R is the polarization mismatch factor between the two antennas. From that, we can now calculate the ratio of received power by transmitted power. That's given by this equation. So here also you see that the polarization loss factor has been ignored, but in simplified form, has been simplified by ignoring other terms. Okay. So a simple, very simple form is takes by lambda square dtdr by 4 pi r square and given by ETER. That's the ratio of received power given by transmitted power. If you know the antenna directivity and antenna efficiencies, you can calculate that. So if you know all these things and if you know the transmitted power, from that you can calculate how much power will be received by your antenna. Is this clear?
Yes.
So it's a very simple equation, but it it correlates or shows how to connect to these two portions: transmit power and receive power. How to connect? Have to have the connection between them. That is all about Friis transmission equation. Now let's see the generalized form. In the previous equation, what we did that we took, we ignored the polarization mismatch factor as well as the reflection mismatch and all this. But if you take all this into account, then you will have 1 minus gamma t square, 1 minus gamma r square, as well as the polarization factor. Then the equation becomes all this. It will be a big equation. Okay. But the simplified equation is still valid because those will be the main components. Okay. And now it says for reflection and polarization matched antennas, the third equation gives you, this is the very generalized form, lambda by 4 pi square, G naught T, G naught R. Okay. These are the gain of transmit and receive antenna. And, this factor you must have come across, this lambda by 4 pi R square is called free space loss factor. This is, in antenna theory and also in communication budget calculation, this is taken as how much will be lost in the space because of propagation. Okay. So this is generally calculated in terms of dB, not in just normal calculation. You will calculate all these things powers calculation as dB. So lambda by 4 pi r square, you must remember, is called loss factor. So that means if you know the frequency or the wavelength and also know the distance between your antennas, you can calculate how much power will be lost in the propagation itself. This is the propagation loss. This is called loss factor. Yeah. So is there any doubt on this? So all of this, is it clear?
Yes, sir.
Yes,
Okay.
yes.
Yeah, now let's come to another important thing. Generally, it is used for the communication itself. In a communication, we have something called noise factor. So you have to calculate how much noise is generated by the antenna. So this terminology says it comes from the noise calculation. If you know, it comes from the temperature, absolute temperature of a device. So it says, it is said that, every object with some physical temperature above absolute zero, that means minus 270 degrees centigrade, will radiate energy. That is a basic rule in, physics. It's called Stefan Boltzmann law that gives you the maximum rate of radiation energy. But this radiation, is given by sigma T to the power 4. Sigma is the sum coefficient and T is the absolute temperature. So yeah, do you remember this equation, or did you heard about this before? What are these radiations?
Yes, yes.
Yeah. So what kind of radiation is being talked about here? Is it the antenna radiation? What are these radiations?
In general, it is used for IR radiations, heat.
Okay. Yeah. Yeah, so it means, it does not have any specific thing. It can be, energy can be in any form. Okay, can be light, it can be, black body radiation, even the temperature radiation, heat radiation as heat. So the simple example is the right side picture shows, because the surface temperature of the sun is very hot, it will radiate. So there you see this radiation is solar radiation, and from the earth it is kind of like, it is cooled down body, very much lower compared to sun. That's why you see the wavelength and all these things, it is shown here. Because in sun the energy is very high, that's why it will be having a very high frequency radiation. Okay, that's why the wavelength is shorter. And because of lower temperature of earth, the radiation is obviously lower energy means lower frequency, right? That will give rise to higher wavelength. I don't know if you remember or not, in physics we had a formula called Wien's formula. So that gives the wavelength as inversely proportional to inversely proportional to temperature. So from the very far away stars and all, their temperature from their color of those stars, we can decide it is in how much temperature. If the temperature is very high, that means it will go towards red, because that will be higher frequency. Okay. And as you move towards the lower and lower body, the radiation wavelength will be increasing. So lambda given by lambda is almost proportional to 1 by T. So now how it is relevant in antenna? Now it says the antenna is the amount of antenna energy radiated is usually represented by an equivalent temperature TB. We have a formulation of TB, or equivalent temperature. So many of the sources surrounding the antenna, they are obviously, because of their temperature, they are always radiating some kind of energy. Okay, all these things equivalently we take their effective or equivalent temperature. Now all these energies will be collected by the antenna or the antenna aperture. So the effective antenna temperature will be given by this integral formula. TA is TB collected over the gain of the antenna over all different angles. All the surroundings, it will collect some energy. For that, the antenna will also have some temperature, and antenna will have some temperature. So that is averaged over antenna gain. So that means antenna temperature is formulated like this. Generally, mostly the antenna makers, they will specify this terminology, TA, antenna temperature. So now how it is relevant? Let's see. So here it shows, the antenna. Here we are talking about receive antenna. Receive antenna is connected to transmission line, and that is connected to a receiver with TR. So all of this you see they have different equivalent temperatures. TR is the receiver, T naught is the for the transmission line, and TP is the for the antenna. Now what happens, because of these different temperatures, the noise will be created. So if you see the formula says the noise power transferred to the receiver is given by for the formula KTA del F. Del F is the bandwidth of the antenna. Okay. So that much noise power will be transferred to the receiver by the antenna. But now because of they are in different temperatures, this calculation is the calculation of TA is not so easy. You have to calculate is as the second equation. So if you see the noise power or noise factor calculation, it takes account of the length of the transmission line as e to the power minus 2 alpha, and also the other formulation or other factors are also taken care. Then finally we have, this is the effective antenna temperature at the receiver terminals. So you see here, note here, there is the temperature not at the antenna terminal, but at the receiver terminal. So that is the temperature what receiver sees as it looks to the antenna. So that's why the modified noise power transferred to the receiver antenna is given by PR equals KTA del F. TA is this formula calculated and del F is the antenna bandwidth. So now why this is relevant? Because of the SNI calculation. In the communication, if we have to discuss, if we have to take the calculation of SNR, because we need BAR, bit error rate, which is calculated from SNR. Okay. So SNR, the signal power is in our hand, we can calculate, but the noise power will be calculated like this. Okay, so that is how we calculate SNR, and we get the noise power from like this antenna equivalent temperature and other temperatures into account. Yeah. So okay, is there any question here? Okay, so if no question, I will move on. So, but yeah, you please remember, because this calculation, although you generally don't see in antenna books and all this, it's there in Balani though, but people don't give much importance. But in communication, these are all very vital for link budget calculation. Okay. So because you need to have the SNR calculation. So for SNR calculation, you need the noise calculation also. How much noise power will be there? So then all this will come into picture.
Sir,
Yeah.
is the noise temperature and the antenna temperature, are they represent the same thing? Noise temperature and antenna temperature? Because there also we take some KTA into B like that. Like TA is the equivalent temperature of provided by the device.
Yes, that is only this temperature we are talking about. But generally, so that's why, yeah, here you see we have defined temperatures in the picture for different devices. TR for the receiver, T naught for the line, TP, that is what you are talking about. Okay. But finally, what we see is the equivalent temperature seen by the receiver. Okay. That is why it is important. Equivalent seen at the receiver terminal. That is given as T in the subscript small a. Yeah, is it understood?
Yeah, yes.
Okay. So this concludes our study of basic antenna. Okay. So properties of antenna and all these things are basic terminologies. Now we'll start the discussion on microstrip antenna itself. Okay. So you must go through all this. If you have any doubt, please come to the next week's tutorial session, and I will be happy to clear any doubt you have. Please go through the Balani's second chapter. I think it's first chapter only. They have lots of examples on gain, directivity, as well as polarization. Please go through that. And then if you have doubt, I can discuss. So now on this thing.
Sir, can you upload this PPT?
No, yeah, but sorry, I cannot do that. But you have all the recorded lectures, right? You have to go through the recorded lectures. Yeah. PPT itself, I cannot give it to you. But go through the lectures is the same only. Okay. Yeah. So before going to the microstrip antenna, so we'll start with microstrip, a overview on microstrip line itself. So why it is important? Because microstrip line, concept of microstrip line precedes that of the antenna. People first talked, they started talking about all this in 1950s only. Then later, the microstrip antenna came into picture. Okay. And why microstrip line is important? Because, it is a planar surface. And this microstrip line is always, taken into picture because we have many circuits nowadays, which is made of microstrip line. Because it is very easily fabricated as a 2D surface. Okay, you can do all the simulation and all, and then fabricate. And it can be done by using photolithographic process. It's a planar transmission line. And the advantage itself is easily miniaturized and integrated with both passive and active microwave devices. So there are passive devices like coupler and all these things, and active devices like transistor and diode. All this also you can connect with this. So it can be used with both of them. So yeah. Now I'll ask you guys. Do you have any overview on this already? Microstrip line. Do you know about the microstrip line? Okay, so that means you don't know. So from the left side picture, can you visualize what is it? Yeah, I guess you have seen about microstrip line before, right? You must have seen microstrip line.
Yeah, we have seen that, but
Yes, sir.
we don't have much. We don't know much about that.
Okay, that's okay. But in the left side picture, can you visualize the top side with this is the metallic strip, okay, the metallic strip, and that is placed on a substrate. Substrate is made of some dielectric of permittivity epsilon r, and the bottom side we have the ground layer. So height of the substrate is h, t is the height of the microstrip itself or the strip, and w is its thickness. So main parameters are w, which is the width of the microstrip line, and h is the thickness of the substrate or height of the substrate. So these are the two vital components. Okay, w and h. So I hope that from the picture, can you understand what w and h is?
Yes.
Yes, sir.
Okay. So now let's see, in the right hand side, we have two other type of transmission lines. See, there are many different type of transmission lines, right? From the basic was two-wire transmission line, and then you must have had parallel plate transmission line. We had waveguide, okay, and then we have microstrip line. We have strip line also. There we have coaxial line. In the middle, it shows a coaxial transmission line, and the right side it shows a one-wire line over a ground. That is another type of transmission line. So now why these are all vital? Coaxial is used many places. Coaxial, in nowadays in our lab also, we use coaxial line. It will be connected for power transmission because mostly it has a 50 ohm impedance match to all the antennas or circuits that we'll be using. Now, why is it vital? So the middle picture, it shows we have a metallic connector in the inside, and there is another metallic layer. In between, we have a dielectric. Mostly it is Teflon. Okay. So structure of coaxial is like that. We have an inner conductor and outer conductor, and in between them we have a dielectric, mostly Teflon. Okay, so inner conductor will be used for the signal propagation, and outer conductor is sorted to the ground. Okay, so now what would be the field diagram? That is what is shown in the picture. If you see the field diagram, this is electric and magnetic fields. It shows like that. In the inner, the red lines are the electric field, and the blue lines are the magnetic field. Okay. So why electric field is like that? Because the inner conductor has the signal. Because let's say this is like positive plus V or minus V, and the outer is sorted. So that's why the signals will be like outward. Sorry, the electric field lines are outward, radially outward. Okay, but this outward is not always like that, because the signal will be like sinusoidal, right? So it will be sometimes outward, sometimes inward. It will be changing with time. But for at a certain point of time, you can take it's like that. And the magnetic field, obviously, it will be what? Curl of electric field. Okay. So from Maxwell equation, the magnetic field can be calculated as that curl of magnetic field equals del D dot E of D. D is the the density of electric field, electric flux density. Sorry. So from that, it will be circular like that. Okay. So these are the field diagrams of a transmission line equation of a coaxial conductor. And in the right side picture, you see, it shows a one-wire line over a ground plane. Okay, so that is shown. There also it shows the field lines. So obviously, if you have a wire like that, so the field lines will be coming back to the ground, and the magnetic field will be obviously the curl of the electric field. That way, it shows the electric field diagram for the one-wire line over a ground plane. So now, why we are talking about all this? So let's see the first one only. If you cut the coaxial line, coaxial line is circular, right? Cylindrical. Now, if you cut the coaxial line outer conductor, it will become like the right hand side, right? The center conductor will remain, and it becomes like this. The ground plane will be, if you cut it like this, in between coaxial outer conductor, it will become like a ground plane in the third picture. Is it understood?
Yeah, yes.
Right. Second picture will become the third picture if you just cut the outer conductor of a transmission coaxial line. Yeah, Nandana and Pavan, is it clear?
Yes, sir.
Okay. So now why we are so much interested? Yeah. Okay. So why are we so much interested about the third picture? Because if you see our microstrip line, it is kind of like that only, third picture. Because here we have a conductor over the ground plane, and in between we are considering there's air. But if you don't have air, let's say you have some other substrate, then will it not be equivalent to a microstrip line? It will be like that. So it means if you make the cylindrical conductor flat, let's make the cylindrical conductor as flat, then it will become like that, isn't it? It will become exactly like the microstrip line. So that's why this equivalence is discussed here.
So can you repeat once more?
The third picture. The third picture shows what? There is a cylindrical conductor over a ground plane. And our microstrip line is also like that.
Yeah.
There is a conductor over a ground plane, but we have some other substrate.
In between substrate.
So here also, instead of air, you consider some other substrate, right?
Yeah.
So that is difference. And another thing is we are taking a cylindrical instead of a cylindrical thing. Let's take a flat conductor. you make the cylindrical structure to a flat conductor, then it will become exactly like the microstrip line. Okay.
Yeah, okay, sir.
Yeah. So this equivalence you always think about. So that's why it is very easy to visualize why all these are, how all of them are connected. Okay. So now says coaxial line, we have a almost like a TM transmission line. So similar TM mode we also discuss in microstrip line also. Okay. And because all of them are now connected like this, two-wire line or coaxial line, we have TEM modes. So that similar TEM mode, or generally it is called quasi-TM, not exactly TM, but it is kind of like TM mode. So it all comes into picture like this because they are all equivalent to coaxial kind transmission line. But what happens in our case is that in the third picture here you see the conductor itself is completely immersed in the air or other. Even in the central conductor in coaxial, it is completely inside a Teflon or other substrate. Okay, that means out in the surrounding of this central conductor, we have only one type of substrate. But in our case, how it is different, you see, in microstrip line, we have two types of substrate. Below the metallic strip, we have epsilon r. Above it, we have AR. Right? That's why it is an inhomogeneous medium, not a homogeneous like the other two. How it is defined. And now, do you understand? How the coaxial and the other one is a homogeneous medium, but in this microstrip line, it is an inhomogeneous medium. Okay, because there are two different type of substrates, AR and the other substrate. Okay, now we will discuss about this, how this is very important or relevant. So, this paper is like very old, as you see, is same as IRD journal in 1955. So there are only, 1955 people have done a historical survey on microwave printed circuits. So that means it was preceded maybe at least for 10 to 20 years. In 1955 only people have done a survey of this thing. So it has been, a lot of research has been done then only. So it shows, there are four different type of transmission lines. Okay, coaxial and then square. So all of them are some kind of distorted or deformed shapes of the coaxial. Instead of a circular, they have taken a aperture, square, rectangular aperture, then a rectangular line or flat strip line. All these are different variants. On the right hand side, it shows how the coaxial line can be converted to microstrip line. So you see the coaxial line, if you like, instead of the central conductor, if you take a rectangular conductor, it will become the second picture. Right side, second picture. And the third picture is our microstrip line. So in what case it will become? Like if you unfold the coaxial line, take the ground into the bottom, then there are, you see the blue picture, there are two different colors, blue and yellow. Those signify there are two different substrates. And in between we have our patch. Okay, so that is how actually microstrip line came into picture. First people had coaxial line, so from that people came into this microstrip line. Understood?
Yes, sir.
Yeah.
Yes, sir.
Okay. Yeah, now let's come to the mode. So what is this mode all about? The mode says what will be the configuration of electrical or magnetic fields in a circuit. To remember, in parallel plate transmission line or waveguide, you have studied about modes, T modes, TM modes, all this. So what are the modes present here? And you know why it is important? Because from modes you can get electric and magnetic fields configurations. You can also see what are the dominant modes. You can calculate the Poynting vector of power density as E cross H star. So that's why studying the mode is very vital. And those are the most basic you can go. This is the fundamental study you can do in any circuit in electromagnetics. Okay, mode. So in microstable line, what happens? We have quasi-TM mode. So let's see what is this all about. So in the left hand side picture you see it shows the field lines. Exactly like it shows almost similar to the transmission line. But now what happens? We have two kind of substrates. In the bottom we have something and the upper layer we have air, right? So that's why the field lines will be different, isn't it? Field lines will, if it was if it was only one type of substrate, then it will be something else. But now in the microstrip line, actually different. So it says the fields are not contained within a particular homogeneous dielectric region, spread both in substrate and air. So that's why it's a non-homogeneous medium. So yeah, now I would like to ask you a question. So do you remember from your basic electromagnetics, if wave propagates from one medium to another medium, in the boundary of these two mediums, what happens? Why phase matching is required in the boundary of these two mediums if wave propagates from one medium to another?
Tangential electric field should be same. Boundary condition.
Yeah, not only tangential. So the condition is there should be the boundary conditions should be valid, should be matched, right?
What boundary conditions?
Right. So now do you remember how the phase matching condition comes into picture from that?
Sir, can you repeat?
So my question is that, yeah, what you said is right. So now if you remember, we had defined conditions, defined studies like perpendicular transmission from one medium to another one, or there was, the S polarization or P polarization, like in the boundary of two medium, we had wave impinging with different polarizations and going in through the other medium. So there also we had the study of boundary conditions and all this. We had some equations, and from that, what were we like actually talking about there? The reflection coefficient and transmission coefficient. That is what we are studying in our basic electromagnetics, right? Do you remember that?
Sir.
Yeah. So if that was there, so what was the phase matching condition? Nandana, yeah, what would be phase matching condition? How does it come into picture in the boundary of two mediums?
Don't remember, sir.
See, these are the very basic things, right? You must know. These are the basic fundamental electronics, electromagnetics. Yeah. See, okay. So maybe, yeah, now I'll tell you. I am not going to write anyway. So what happens? Generally, we calculate what? Tangential electric field should be equal, right? In the boundary of this two mediums, what would happen? We take the tangential electric field as equal, and also we have conditions of, the tangential magnetic field also we have some condition, all this. So now let's say the tangential electric field only, we equal in two mediums. So what happens there? How the electric field is described? We take A into e to the power j theta form, right? A is the magnitude and e to the power j theta is the phase of the electric field in one medium. Okay, so now it has to same with the other medium. Let's say A1 e to the power j theta 1 equals B1 e to the power j theta 2. But the B is for the other medium. If we equal these two, right? So obviously what happens? Now A e to the power j theta is B equals e to the power j theta 2. That means this j theta 1 should be j equals j theta 2. Otherwise this equality will not be valid, right? Amplitude must be same. A equals B. That is obvious. Then only it would be same. But along with that, this e to the power j theta term has to be same. Only when what? J theta 1 should be j theta 2. Do you understand what I am talking about?
Yeah, yes.
Nandana?
Yes, sir.
Yeah. So in the boundary, I am saying let's express the tangential electric field as A into e to the power j theta A in one medium. In the other medium, B into e to the power j theta B. So if both of them has to be equal, then what happens? A magnitude A should be magnitude of B, and the theta j theta term has to be same. So this is only called phase matching condition. Okay.
Okay, sir.
Right. This is phase matching condition. Now let's see. Now let's come back to here, because in our microstrip line we have interface or boundary between two mediums. That's why it all comes into picture. Now it says if you have TEM, if you just consider a simple TEM field, then what happens? In the boundary, the phase velocity should be different between two mediums. So obviously the phase matching condition will not hold. So that's why the simple TEM model, TEM mode will not work here. So that's why it says microstrip line cannot support a pure TEM mode. Do you understand this? Because if it was only one substrate, the same TEM mode will happen, But because the wave is same, right? But the medium is different. So, but that's why if the same TEM field will have different phase velocity in different mediums. So that's why the phase matching condition will not hold. Do you understand this point?
So one more time. This one.
So it is saying why a simple TEM mode cannot exist in the microstrip line. Because if a simple TEM mode is there, that will lead to one type of phase velocity or one type certain phase in the substrate below the string, and another type of phase velocity or another phase in the air. So then obviously the phase matching condition will not hold. If the wave propagates between these two medium, if the phase matching condition does not hold, that means boundary condition does not hold. So that means obviously the wave does not exist. It does not follow the Maxwell's rules. That's why a simple pure TEM wave cannot hold here.
Okay.
Now it says, the dielectric substrate is very thin. That means H is, smaller, very small to lambda. And the fields are essentially same as static DC case. Because it's very small, the field profile will be almost same as static case or DC case. And also the TEM mode has a cutoff frequency of 0 at DC. So normally TEM mode can propagate above DC only. And in this case, we have quasi-TEM modes. So it almost behave like TEM, but not exactly TEM. That's why it's called quasi-TEM. Okay. So it is mostly valid at low frequencies. And the EZ, so this says when the frequency tends to 0, all the EZ and HZ components become 0. So EZ and EZ are what? Longitudinal components if the direction of propagation is G. So that's why then it becomes TEM or transvert mode, because longitudinal components are 0. So that is the is the essence of quasi TM. But although it happens only at the asymptotically 0 frequency, but mostly it is valid around a few gigahertz. Around a few gigahertz, all these equations or TEM modes, quasi TM modes are valid. So we can take almost a TEM like analysis of microstrip line. And we will see the same analysis is valid for microstrip antennas also. We do this low frequency analysis and we see that up to a few gigahertz it is valid. Yeah, any doubt here? So we take this discussion from microstrip line and now we move to microstrip antennas. Okay. I hope you understood how microstrip line is working, how this electric field lines and magnetic field. So this you remember the field diagram here. So the solid lines are electric field and dotted are magnetic field. These you must remember here because these will be discussed in antenna also. It's just like if you have a positive charge in the top and negative charge in the bottom ground, then how the field will move. The field lines is almost similar to that. So these are the static TEM parameters of microstrip line. These all are taken from the book Pojar. And if you see microstrip line, we have the equivalent model is given as we have a substrate ER and AR, but equivalently we take as if it has a other substrate and microstrip, the strip is inside a substrate. So what is this substrate called? It has permittivity of epsilon E, or that is effective permittivity. That is a very important parameter of microstrip line. That is how we take all this discussion or analysis is done for microstrip circuit. So this is calculated as epsilon, the formulas are all given. And the characteristic impedance for this transmission line is given. Same for phase velocity and propagation constant. So now always you notice that we are taking the epsilon E. Generally what we take, phase velocity we take epsilon R, the permittivity of the medium. But here we have two defined medium boundaries, right? That's why the effective permittivity is taken always into consideration. That you must remember in microstrip line. You should have the value of effective permittivity. So these equations are very vital for all the calculations in microstrip line. Okay. Any doubt here?
No.
Okay. So maybe this is about the microstrip antenna. So why microstrip antenna is very important and all. In the right hand side, you see this is the first version of microstrip antenna. Was designed by French engineer Deschamps in 1953. So he had this kind of array designed already, conformal array. And I think he also holds the first patent, for microstrip antenna in that is 1960s, I suppose. So why it is important? Why we are talking about microstrip antenna so much? How it is important? So he says high performance aircraft, satellite or missile or everything, even wireless communication, size, weight, cost, performance, and ease of installation is a very vital part. and also aerodynamic profile are the constraints. And that's why low profile antennas are required. You cannot just install a big horn antenna on top of the aircraft, right? So we need a planar circuit most of the cases, which are very easy to install, and it has the very simple profile. That's why how microstrip antenna became so important. It has a low profile and is conformal to planar and non-planar surfaces. How it is planar? It is obviously structure, and non-planar also it can be conformal because some of the substrate it is such like that something I remember is called taconic. There is substrate called taconic. If you have designed microstrip antenna on that, that can be even folded, right? So there are other antenna, foldable microstrip antenna also. So it is simple and inexpensive because of very easy to design also. It is mechanically robust when mounted on some surface because it's planar. It does not nothing hums it much. Compatible with MMIC design, monolithic designs, and versatile in terms of resonant frequency, polarization, pattern, and impedance. You can design the antenna for many different factors, for many different resonances, polarization, and other things. And you can add variable loads like pin and vector diodes, and it will lead to adaptive elements with variable resonant frequency, impedance, and all this. So microstrip antenna also can be tuned using some diodes. So that's why that it is so much ubiquitous nowadays. Everywhere you can see talked about microstrip antenna and all. So maybe you will let it be here. From next class we'll start from this. Okay, we'll start from the microstrip antenna basic analysis and all. Today we'll end it here, and so I'll request you guys to look into some examples of polarization and gain calculation in Balani's book. And if you have any doubt, please come to the tutorial session Saturday morning. Okay. So okay, then bye. See you next
Okay,
week.
sir.
Yeah.
Bye, sir.
Yeah.